Yes, so welcome everyone to the second lecture in the Advanced Topics in Quantum Information Theory course. I'm going to begin with a sort of run through of what we discussed last time to refresh your memory and to set the stage for what we do today. So in the last lecture, we started by discussing the energy eigenbasis, which is essentially the most important manner of looking at the density matrix of a system that we have. We discussed energy level diagrams, which is essentially the manner of converting the Hamiltonian into a set of energy levels that we can look at. So for instance, if we have a Hamiltonian of a qubit, which is 0, the projector on the state 0, plus E on the state 1, plus let's say 3E on the state 2, then this can be written as an energy level diagram of this form, where this is the state 0, this is state 1, and this is state 2. And such diagrams will become quite useful when we are constructing different scenarios. We discussed the concept of diagonal states and incoherent states of a system, which essentially mean that the density matrix, when we write it in the energy eigenbasis, has no diagonal elements between different energies. When it comes to diagonal states, it essentially means whatever basis we've chosen, it's entirely diagonal. So there's no off-diagonal elements at all. We discussed the concept of the average energy, which is simply the trace of the Hamiltonian times the density matrix, which when we write it in terms of the diagonal elements of the density matrix in the energy eigenbasis, is just the linear combination of the energy eigenvalues. So these, remember, are the diagonal elements of the density matrix in the energy eigenbasis, and they're called populations. Okay, so from there we went on to discuss the simplest operation, which is the unitary operation, the properties of the unitary operation, essentially, most importantly, that it preserves the entropy of a system, and that it can be written as the exponential of a Hamiltonian. And then we looked at the special class of unitary operations, which we called energy preserving operations. These are those that commute with the Hamiltonian of our system. And the result was that they preserved energy, which is not only that they didn't change the average energy, but also that essentially they can be written as matrices themselves. They can be written as block diagonal in the energy eigenbasis of the Hamiltonian. And I expect today you discussed a tutorial problem related to that concept. Okay, and then we shifted to discuss the basic building block of our thermal machines, which is the virtual qubit. So we started from the thermal state of an actual qubit, but we were able to conclude that if you are given any state of a qubit that is diagonal in energy, then you can always associate a temperature to it by simply taking the ratio of the excited state population by the ground state population and matching it to the Gibbs ratio of the Gibbs ratio, essentially defined by a virtual temperature and an energy. So once you know the Hamiltonian of a qubit and you know the populations of the ground and excited state, that essentially fixes the temperature for them. And what this means is that even in more general higher dimensional states where you might not be in a thermal state to begin with, you can still isolate particular pairs of energy levels, and by looking at the ratio of populations, understand what temperature they appear to be at. And this is a concept. Why this is useful will become clearer the more we do in thermodynamics. The properties of a virtual qubit, which is this subspace, you can look at it in terms of the difference in population Z, which is the ground minus the excited state population. Well, for real qubits, it's just this. For virtual qubits, you have to divide it by the norm of the population. And remember, the norm is just the total population in that subspace. And of course, you can look at it as you can look at the virtual temperature itself. Z and the virtual temperature are related by this simple formula that Z is the hyperbolic tangent of beta times the energy. Now I say E here, but E always refers to the difference in energies between the top energy level and the bottom energy level of the virtual qubit. So this is something that's very important. When we look at the virtual qubit and virtual temperatures and such properties, it's always the ratio of populations that matter, and it's always the difference in energy that matters for our formulae. Okay, and then we ended with, I started towards the end of the lecture by discussing the concept of composing two virtual qubits together. Right, so that was where we got to last time. And all right, I'm going to open the notes now that I have. Okay, so at the end of last lecture, we talked about composing virtual qubits, and I got the sense that perhaps the tensor product state structure is not something that people are very much used to. So I just want to briefly go through it now before I discuss again composing virtual qubits in particular. And so imagine now that I have, this is not so much a virtual qubits as much as a general picture. I have two states, two systems, A and B, and two states that I write as rho A and rho B. And I express them in terms of the density matrix as rho A 0, 0, rho A 0, 1, rho A 1, 0, rho A 1, 1. Now, remember, whenever we write the density matrix, this is always with respect to some basis. So in my mind, what I'm doing is I'm writing I have a basis in mind for A. And for every bra and every ket of A, I have a density matrix element. And what this means is that rho A mn is just given by the inner product of the state with that bra and that ket from the basis that I've chosen. So for example, rho 0, 1 is the inner product between 0 and 1 of the state rho. Okay. And I have a similar thing for rho B, of course. So now what happens when I take the tensor product rho A tensor rho B? Now I have a new basis. So the basis of states now is 0, 0 on AB, 0, 1 on AB, 1, 0 on AB, and 1, 1 on AB. So if I had, so for example, I could also write rho A in bracket notation as rho 0, 0, 0, 0 plus rho 0, 1, 0, 1 plus rho 1, 0, 1, 0 plus rho 1, 1, 1, 1 with A's all over the place, appropriately placed. And I have a similar thing for B. So we know that when we take rho A tensor rho B, I simply tensor product all of these together. Now, I haven't said this explicitly, but very often, but almost always, I will use this shorthand notation when we have A tensor B to simply put it both in the same ket with the understanding, of course, that A is before B. So it's always clear from context what the notation is. So this will simply take all of these elements, tensor product the corresponding elements in B. So I will not list out all of them because they're going to be 4 times 4, so there are going to be 16 of them. But imagine that I wanted to look at the element that is associated with the following. So I want to focus on 0, 1, say 1, 0, AB. This, of course, is equal to 0, 1, A, 1, 0, B. And I know that this in the original density matrix had rho 0, 1. And so this in the density matrix of rho B will pick out rho 1, 0, B. So the element associated to this will be rho 0, 1, A times rho 1, 0, B. And so what we get is that every element in the density matrix that is the tensor product of these two states is just going to be the product of the corresponding elements in the original state. So as a result, this written as a density matrix is going to look like the following. So keeping in mind again that the basis that I'm working with is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. I'm going to have the states here is going to be 0, 0 on A, 0, 0 on B. Here, A is still 0, 0 because it's this one and this one, but B is now 0, 1. Here instead, I still have 0, 0 on A, but 1, 0 on B. Here 0, 0 on A, and here 1, 1 on B, and so on and so forth. In fact, what I can see, another way of looking at it, and the reason I split it into 4 blocks is because each block is essentially the density matrix of B multiplied by the corresponding element of A. So this entire block is going to be row 0, 1 of A, which is just a number, times the density matrix of B. This is going to be row 1, 0 of A times the density matrix on B. And this is row 1, 1 of A times the density matrix of B. Okay. One important thing to note is that the diagonal elements, as you can see, are products of the diagonal elements of the original density matrix. So we have row 0, 0, 0, 0, 0, 0, 1, 1. In this spot here, I'm going to have row 1, 1, row 0, 0. And in this spot here, I'm going to have row 1, 1, row 1, 1. And this is why I made the statement in the last lecture that if we have density matrices that are written in the energy eigenbasis, which is almost always what we work with, then the diagonal elements are the populations. And so in the resultant tensor product state, the diagonal elements of that, which are the populations of the tensor product state, are going to be the product of the individual populations. So as an example, if I had 2 diagonal density matrices, let's just say this was some RA, 0, 0, 1 minus RA, and row B was RB, 0, 0, 1 minus RB, 1 minus because of the trace condition, then row A tensor row B is going to simply be RA, RB, RA, 1 minus RB, 1 minus RA, RB, and 1 minus RA times 1 minus RB, with zeros in all of the other places. Right. Is there any question regarding this process? Nope. All right. Very good. Okay. So let's continue with what we wanted to do, which is to compose virtual qubits. So, sorry, let's not scroll too fast. Imagine now I have 2 systems, well, still the same 2 systems, A and B, and I have a Hamiltonian of A that I describe by some sort of energy level diagram. I have a Hamiltonian on B that I describe by another energy level diagram. But what I want to do is I want to focus on this virtual qubit on A, and let's say this virtual qubit on B. And I want to look at, in the tensor product of the 2 states, I want to look at how this virtual qubit looks like. So this is now equivalent to the following. I'm now going to focus on just these energies. So I have the energy gap EA between these 2 states. I have the energy gap EB for the Hamiltonian B. I take the tensor product of them, which means that I end up with the energy gap A, EB, and this. So I'm going to call these states 0, 1. So they're not actually 0 and 1 in the original states, but it's not going to matter for our purposes. 1, 0, and 1, 1. Okay, now let me explain how I get this energy level diagram. Oh, sorry, that was the wrong. That's EB, that's EA, and yes. Right. So let me explain how we get this energy level diagram for the joint state. So what I've done here is I've essentially claimed by drawing this figure that the energy eigenvalues in the joint Hamiltonian are the sums of the energy eigenvalues of the individual ones, and this is This is because energy is an additive quantity. So if I have two systems A, B, the Hamiltonian of the joint system is given by the sum of the Hamiltonians, the original Hamiltonians, which in our case is HA, written as a joint operator on both. So it's HA tensor nothing on B plus nothing. Well, by say nothing, I mean the identity operator tensored with HB. So energy is an additive quantity. The total energy of the system is the sum of the two energy levels, which means that if I take a state, an energy eigenstate EM on A, which so it has the property that HA EM on A is equal to EMA, the eigenvalue times the state. And a similar thing for B, En of B, such that HB En of B is ENB, ENB. Then what I'm going to get is HAB acting on the tensor product of these two energy eigenstates. And you can do this by substituting the values, but what you will see is you simply get EMA plus ENB, because in the first case, HA acts to give you the first eigenvalue on A, and this next case, HB acts to give you the other eigenvalue times the original state. So this is just to reinforce the fact, in case you haven't seen this before, that when you take two energy eigenbases, the energy eigenbases of two systems, and then you look at the joint Hamiltonian, if it's just a sum, this is in the case that there's no interaction Hamiltonian between them. But if it's just the sum of the original Hamiltonians, the energy eigenstates of the joint system are just the tensor product energy eigenstates, and in the energy eigenvalues are the sums, pairwise sums of the original energy eigenvalues. Which is why in this diagram here, I started with these local energy gaps and I simply added them. So between 0, 0 and 0, 1, I simply have the gap EB. Between 0, 0 and 1, 0, I have the gap EA. So that's this gap. And then finally, between both of them being in the state 0 and both of them being in the state 1, I'm going to have the gap EA plus EB, because of course, this again is EB. Okay, right. So what do I know? I assume in the first place that for the individual systems, I know the virtual temperature on A. So I know beta VA. Essentially, I know the Gibbs ratio of this energy gap. And the same way, I know the virtual temperature on the virtual qubit of B that I've picked. So this is to say, if in the density matrix of the system A, I had populations, I'm going to call this P0 of A and P1 of A. And here I have P0 of B and P1 of B. Then I have the following expressions. I know that P1 of A upon P0 of A is equal to e to the minus beta VA EA. And the same thing for B. P1 of B upon P0 of B is equal to e to the minus beta V B EB. Okay. But okay, so my interest is now to look at the virtual qubits in this new diagram in the joint state and ask, well, what are the virtual temperatures that I see there? Now, there are 4 different states. I have, well, 1, 2, 3, 4 of them. So there are 6 different ways to combine them as pairs. And out of this, in fact, 4 of the ways are quite simple, which they won't give us anything new, because what you see is if I take the pair to be 0, 0 and 0, 1, for instance, this is essentially the same as the virtual qubit on B, but just tensor product with the state 0 on A. So A doesn't change, it's just B that changes. The same thing goes for 1, 0 and 1, 1. So we're going to do this in detail here. So I have now, so rho A is of the form, it's got many elements that we don't know about, but we know that we have a rho 0A and a rho 1A that correspond to, let's call this actually not rho, because they were populations. Let's they're all P's actually, yeah. So P0A and P1A corresponding to those two states that we have picked from the original Hamiltonian. And the same thing for B. So rho B is given by something with a P0 of P and a P1 of P. And so therefore my rho AB is going to have the following form. So there are going to be many states we don't know about, but then there's going to be a rho 0A, rho 0B. There's going to be a rho 0A, rho 1B. There's going to be a rho 1A, rho 0B. I keep saying rho instead of P, I apologize. And a P1A, P1B. This is associated to 0, 0, to 0, 1, to 1, 0, and to 1, 1 on AB. Okay, so let me draw this again here so that it's always with us when we're discussing. 1, 0, 0, 1, 1, 1. So the first thing I do is I pick the states 0, 0 and 0, 1, AB. Okay, so the energy delta E of this is basically just EB, because the energy of A is still the same. So this is now just a difference between the energy eigenstates of the B system. The population P00 on AB is equal to P0A, P0B, and the same thing, P01 on AB is very simply P0A, P1 of B. So to find the virtual temperature, I just have to solve the following equation. I say, well, the excited state population, P10 of AB divided by the ground state population of that virtual qubit should be given by the exponent of the virtual temperature, in this case, times the energy difference, which is just EB. But now if I simplify the populations on the left, I know that they are products. So this is just P0, P0, AB divided by P0A, P1, oh, sorry, mistake. P1, P0B, P0 cancels, and this is now P1B upon P0B. But this by definition, we already know is the exponent of the virtual temperature of B times the energy gap of B. And so now if I just look at this equation here, I have very simply beta V, at least corresponding to the pair 0, 0, 0, 1, is just beta V B. So what we find is, let me write this as EA. So what we find is that this pair has just the virtual temperature of B, which kind of makes sense because as we discussed on the top, this virtual qubit is essentially just the original virtual qubit of B tensor product with the state 0 of A. Yes, so we can repeat this for the upper two states as well, and we will find exactly the same because these are simply the two. This is really the virtual qubit of B, but tensor product with the excited state of A. And then we can do the flip side. We can conversely look at this energy level and this energy level, but this now gives us the other thing. So if I look at these two, then I see that they are exactly the same as this one, just tensor product with the state of 0 on B. And so as expected, if we do that calculation, we will get that virtual temperature, so I'll mark it like this, is the same as the virtual temperature of A, and the same thing for this virtual temperature. It's the same as A. So out of 6 different pairs, 4 of them are just the original virtual qubits, tensor product state on the other system. So there are only 2 pairs that actually give us interesting or non-trivial answers. And the pairs are, so the non-trivial ones, non-trivial virtual qubits are the, I'm going to call this beta V plus, which corresponds to the states 0, 0, and 1, 1, because both of the states now are changing 0, 0 to 1, 1. And then there's a beta V minus that corresponds to 0, 1, and 1, 0. So both of them flip, but the opposite way. So let's do beta V plus first. Okay. So the energy of the state 0, 0, sorry, This is not the way I want to do it. So the energy gap corresponding to 0, 0, and 1, 1 is, just by inspection of the figure, is the sum of the two energy gaps. Because if you go from the state 0, 0 to 1, 1, both A and B go to the excited states. So the energy difference is the sum of the two energy differences originally. And the population P00 is P0 times P0, and P11 is P1 times P1. So AB, A, B, A, B. So this now gives us a formula for the Gibbs ratio, which is, so P11AB upon P00AB should be equal to the exponent of that virtual temperature plus times the energy gap, which is EA plus EB. And this in turn is equal to P1A, P1A, P1B upon P0A, P0B. And each of these now I can replace by the Gibbs ratio from their original virtual temperatures. I know that the ratio P1 upon P0 for A and for B are given by these Gibbs ratios just by construction. So now I just look at the exponential parts of this equation. So this part here, and I can take it out of the exponent. On both sides, I take the log. And what I get is beta V plus times EA plus EB is equal to beta VA EA plus beta VB EB, which essentially results in beta V plus is beta VA times EA upon EA plus EB plus beta VB times EA upon EA plus EB. The reason I've written it in this form is that these two numbers that are multiplying the virtual temperatures, they're essentially just, not even, yeah, that's equal to P, that's equal to 1. It's just a number between 0 and 1. So what we see is that the virtual temperature of this transition from the bottom of the 4-qubit subspace to the top of the 4-qubit subspace, that virtual temperature is a convex combination of the two original virtual temperatures that we had. And as a result, being a convex combination of the two virtual temperatures, it is guaranteed to lie in between the two. So beta V plus is within the range of beta VA and beta VB. Now I can't write the interval without knowing which one is greater, A, the virtual temperature of A, or the virtual temperature of B, but whichever way it is, this number beta V plus is always going to be in between. So this is interesting, and it will come in useful for us. But the even more interesting one is the other one. So now I'm going to look at, let me draw it again. Sorry, yes, the question?
Next to beta B, B, it should be EB.
Oh, yes,
right?
Thank you. You're right, thank you. Mistake there. Oh. Good, paying attention. Thanks very much. Yes, so let me draw this again. Now, 0, 0, 0, 1, 1, 0, 1, 1. And we've just looked at beta V plus, and we are finally going to look at beta V minus in these two intermediate states. Okay, so yeah, so when we look at the energy gap delta E of this 0, 1 and 1, 0 space, what is this equal to? This is the energy of the higher energy is 1, 0 on AB, and the lower energy is 0, 1 on AB. But this is essentially EA minus, I've been using. So I apologize for the fact that my subscripts and superscripts keep jumping according to when I need them to be one or the other, but I hope that from context it's very clear that when I use A and B, it's just referring to the systems A and B. Right, so that's the difference in energies, and the population P So the population P01, I'm not going to write this down because it's the same. So let's look at now the Gibbs ratio. So e to the minus beta V minus times the energy gap of this transition is given by P10 AB upon P01 AB, which is P1A P0B upon P0A P1B. And again, I can use the fact that it's a Gibbs ratio. P1 upon P0 and A is e to the minus beta V A EA. But P0B upon P1B is the inverse. So it's e to the plus beta VB EB. And so now I do the same thing. I look at the exponential, I take the log, and I get the following equation: beta V minus times EA minus EB is equal to beta V AEA minus beta VB EB. And so beta V minus is this, beta V AEA minus beta VB EB upon EA minus EB. And here's the interesting thing, just like the original form, the previous formula with beta V plus was guaranteed to lie in between the two temperatures, this is the number that is guaranteed to lie outside the range of the two temperatures. So I'm not going to go through the calculation now, but it would be easy to check that if you look at beta V minus beta V A and beta V minus beta V B, these differences, they will both be of the same sign, which means that beta V minus is either greater than both of the temperatures or less than both of the temperatures. So on the axis, essentially of beta, so this is beta VA, and let's assume that beta VB is the higher one, so it's the colder one. Remember that with beta, the higher beta, the colder it is. Beta V minus is somewhere in this range. And this makes beta V minus the sort of the foundation of all of our thermal machines, because remember, in thermodynamics, if you're given two temperatures, it's very easy to create a temperature that is in between. We just bring two objects of different temperatures in contact, and we will have heat flow and some intermediate temperature will arise. But the key of all of the machines that we know, engines and refrigerators, is to create temperatures that are outside the range that we begin with. And this is essentially an example of how to create that. If you have two thermal states of qubits and you bring them together, in the joint state of these two qubits, there is going to be a subspace that has a temperature that is outside the original temperatures that you began with. Okay, a few more points to say here is that essentially this quantity, which is very important to us, I will place it here to begin with. Oh, sorry. This is not really bounded. So beta V minus can be made to be anything between minus and plus infinity if we are able to tune the energies EA and EB. And the reason is because this thing in the denominator, EA minus EB, if it's small, then you can see that beta V minus approaches minus infinity or plus infinity. So this is something that's written in the lecture notes in more detail, but you can easily do a little exercise to see that tuning EA and EB to be certain values, you can get beta V minus to be as large as you like or as small as you like, including negative values. All right, at this point, I would pause to ask if you have any questions or comments of any kind. Yes?
Question regarding if beta V minus becomes negative.
Yes.
Is that just because we, or can this be fixed by simply swapping EA and EB so that the temperature again becomes a positive value?
No, that's a very good question. So, right. So actually, it's a very good question because I could talk about things that perhaps I should have mentioned before. So the positivity or negativity of the temperature of beta corresponds to whether as you go higher in energy, there is less or more population. So when the temperature is positive, it means that as you go to higher energy levels, the population keeps decreasing. And this is because of the fact that if you have, let's say if you have a P1 upon P0 is equal to E to the minus a positive temperature times a delta E, which is positive because you've ordered it as P1 upon P0, then this is going to be something that's less than 1. So positive temperatures means you decrease in energy. You decrease the population as you go higher in energy. Negative temperatures means the opposite. So this is actually called an inversion. So negative temperature is called an inversion because you have something that you don't usually have, which is that a high energy level has a greater population. Now, the temperature is not, you cannot switch from negative to positive temperatures by swapping the label, because what happens is the temperature is defined by the population in J upon the population in I is equal to E to the minus beta Ij times Ej minus Ei. So if you were to swap the labels, you would get Pi upon Pj is E to the minus, let's just call this beta Ji, Ei minus Ej, but this is the same equation because you flipped both the ratio on the left and you flipped the sign of the two, the energy gap is now flipped in sign. So this gives you that beta Ij is equal to beta Ji. So this is a nice thing about the virtual temperature. Even if you relabel the energy levels, you're not going to get a different virtual temperature. And what this means in practice, returning to your original question, if we get a negative temperature, it essentially means that the population in this state, P10, is greater than that of P01. So P10 greater than P01 is negative beta V minus. So that's an actual physical fact. It's not something that can be changed with relabeling mathematically. Yeah. Does that answer the question?
Yes, thanks a lot. That was yeah, it answered exactly my question.
Perfect. Thank you for the question. Yes, and in fact, and just to say this, the basis of making a refrigerator is to make a very high value of beta, because a high value of beta is a low temperature, which is to make a virtual qubit where most of the population is in the ground state. Because then when you connect this to external systems, it will induce, and this we will continue with the next thing that we do, will induce the external systems to also go towards the ground state. But when you want to make an engine, and remember the basic concept of an engine is if you have sort of a ladder and you want to raise a weight up this ladder, then you need the opposite. You need to have a virtual qubit where you're more likely to be the excited state than in the ground state, so that when you connect it to an external system, it induces the external system to also move up in energy. So that's the meaning of a negative temperature. It's the basis of engines, just like a positive temperature is the basis for refrigerators. Okay. Right. So the next thing that I would like to do now is, so then maybe this would be a good point to actually take a break, because I will shift now from virtual qubits to doing the basic building block of the operations that we have in thermodynamics, which is the qubit swap operation. It's effectively the simplest possible unitary operation that you can pick. That's not just the identity. So I will take a break now, and when we come back, we will continue with doing the swap operation. Before I continue with the lecture, I also have something to say about there is a campaign in ETH about that regards the mental health of students and staff. So I will talk about that as well. But anyway, let's wrap up now and return at 4:35 or 16:35. I will be back before that to answer questions, but the lecture continues at 16:35. All right.
I guess what I mean is that, like, so you have a Hamiltonian which is delta 1, 1, right? For example.
Yes.
Yeah, and then you say, okay, but I don't want one to be I don't want one to be excited state. I want one to be ground state. And then the Hamiltonian is delta 0, 0.
Okay, so do you change the Hamiltonian to delta 0, 0? Okay, yes.
Yes. But then you kind of, so essentially you only change the labels of the bases.
Yes.
But kind of the energy stays, does then the beta change the sign?
No, because so if I have Hamiltonian is that, then my tau is going to be, so in the 0, 1 basis, it's going to be e to the minus delta beta 1, and this of course with the partition function on the outside, because now the 0 is going to be the high energy state, it's going to the thermal state, for example, of this. So I still have that beta is defined from, so P0 over P1 is equal to e to the minus beta times E0 minus E1, or the opposite, I can say P1 upon P0 is e to the minus beta E1 minus E0, and these are the same equation. And so this is now e to the minus beta delta is equal to e to the minus beta E0 is the higher one, delta. I mean, this is to say it's still going to be, it's still the beta that I get is still going to be the beta that appears as sort of the temperature of the thermal state. So it will not flip the sign. So in the case that I just described here, I could just swap, if I swap the labels of 1, 0 and 0, 1 and call them anything else, I will still get beta V minus to be the same, because it's just whatever label I put, the first state that is labeled minus the second state that is labeled, the energy's difference will be related to the ratio of the first one upon the second one. So beta should always remain the same. And this is kind of important because otherwise the notion of positive temperatures being, energy population decreasing with energy and stuff would not hold if it would flip the sign under any of this relabeling. Okay. But one thing I want to end with is just to say that the convention is always to use, independently of this, is to keep ground state as being 0, and because ground state essentially, otherwise all of the language will become confusing, independently of discussing relabeling. Yeah.
Okay.
Okay, so right, so the first thing I would start with is that I would like to inform you about, let's take this and put it in the chat. So ETH at the moment is having a campaign for students to pay attention, well, students are everybody essentially, to pay attention to their mental health, because as everyone will have realized by now, the pandemic exacerbates any existing problems that we might have with our studies and our lives. And so I've put in the link in the chat to a webpage that I think would be interesting for you to check out. And it's essentially a webpage with a lot of information about what to do if you are having trouble handling either stress or not only things related to your studies, but also with your personal life. If you're having any sort of difficulty dealing with things on a mental or emotional level at the moment. And so on the website, I've not shared the screen of the website, but on that you can find a lot of information that is useful to read. But specifically an important thing to do is, if you look at the where can I find help of that website and the help and contact points inside and outside ETH Zurich, you will see links for counseling for students and counseling for doctoral staff. And the most important link in that is the psychological counseling service, which is shared between UZH, the University of Zurich, and ETH Zurich. So it's open to all students and doctoral students at ETH and UZH. Yes, so I would, well, there are other links as well. For example, there is a link to MeWell, which is a community that was founded last year. I was actually involved in the first couple of meetings when they were founding this, which is just a community of students and staff that get together to organize events and act as a support group for each other in case somebody's having trouble. But of course, this is not to replace professional help if one is in a situation where you believe that you should get professional help. I think the main thing to say about all of this, the upshot, is talk about it, in the sense that if you find yourself in a situation like this where things are hard and you're finding it hard to deal with stuff, don't let yourself be isolated. Reach out to friends, to family, and in cases that require more intervention, reach out to professional help, to the psychological counseling service. Don't let yourself be isolated by the situation that you're in. This is especially true right now because, as we all know, the pandemic tends to make everything that we used to have in our lives to may feel better, like our activities and contact with people that we like, just makes all of this much harder. So I expect that many of us are finding it harder to do everything now than they were, let's say, a year and a half ago. So yes, pay attention to your mental health and take care of yourselves. That is the most important message to be taken out of this. Okay, let's continue now with the lecture. And now what we're going to do is we're going to shift track. We are going to talk about, first we're going to make sure that my Apple Pencil works, without which I cannot explain anything. Yes. Very good. Yes, so we're going to talk about the simplest possible unitary operation, the qubit swap. Just like the virtual qubit is sort of the building block for more complicated states and the thermal properties of more complicated states, the qubit swap is essentially the building block for more complicated thermodynamic operations. And in fact, there are some very general and very powerful thermodynamic operations that depend on just repetitions of this singular swap. So the way I'm going to explain the qubit swap is via the following. So let's imagine now that I have just, as I said, 2 qubits. So I have HA with an energy gap of EA, HB, then energy gap of EB. And I start in diagonal states. So I start with rho A equals, so actually, in fact, I'm not going to use A and B here, but I'm going to start differentiating between the system and something that I will refer to either with respect to as a virtual qubit or as the machine, to sort of give you the impression that there is one system on which we wish to perform a thermodynamic task, and then there is another system that helps with it in some fashion. So I have rho S, which I will write with these. So PS 0, 0, 1 minus PS, and rho V, which is given by the density matrix PV 0, 0, and 1 minus PV. So these are real qubits at the moment. They're not virtual qubits. The reason that you can see they're real qubits is because the density matrix is fully normalized. So all of the population is in them. And I have the tensor product state, rho S tensor rho V. And I perform the following unitary operation, which is swap. So there are 2 ways of looking at it. One is to say I swap the states 1, 0, and 0, 1 of SV. And the other way is to say I swap the full state. Okay, so this unitary is given by the following matrix. It's 1, 0, 1, 1, 0, 1. So remember again, 0, 0, 0, 1, 1, 0, 1, 1. So this is effectively the 2-qubit generalized form of the X operator. Remember the X operator which you use to flip the computational basis states of a single qubit is just 0, 1, 1, 0. And this is essentially an X operator sitting in a subspace. But the effect that it has is effectively to flip the 2 states, because what I start with, so I start with rho S tensor rho V, which is using what we already know. This is PS PV, PS 1 minus PV, 1 minus PS PV, and 1 minus PS times 1 minus PV. And what this is going to result in, so if I look at U rho S tensor rho V U dagger, because this is the final state. This I can call rho, should have used subscripts, rho SV prime. This is going to be the following state. I'm not going to go through the entire calculation, but suffice to say that the same thing happens as you would expect in the case of X acting on a qubit. You just flip the populations of those two states. So I get PS PV still remains the same. 1 minus PS, 1 minus PV still remains the same, but the middle two flip. So I get 1 minus PS PV and PS times 1 minus PV. But what this looks like, I mean, now this I can again write it as a tensor product state. And this is the following. This is now PV 1 minus PV tensor PS 1 minus PS. But this is now on the state S, and this is now on the state V. So what I have essentially is that the states of rho, the states of the system and the other system, which I call V, have simply flipped in this as a result of this operation. So just as a side note, if I was doing this for a higher dimensional system, so if I had S and V to be, not just two-dimensional, higher dimensional, then the unitary would essentially be the change of basis where every ij of system and machine would flip to ji of the system and machine, which incidentally, if I and I are the same on both of them, you get nothing. So this is the generalized swap that will cause both of them to flip. In our case, it's just, there are just two states that have been flipped, 0, 1 and 1, 0. Okay, so this is the qubit swap. Now, clearly, since the states completely flip, the properties of the state at the end of the system in particular are simply the properties of whatever the properties of whatever the other system V was in the beginning. So what I can say is rho S prime, which is the final state of rho of S. So remember, whenever I use prime, it simply reflects the final value of either state or a variable at the end of a transformation. This is going to be the partial trace of the final state of S and V traced over V, which is the trace over V of, so essentially now I have, if I label it as rho 1, if rho S V initial was rho 1 tensor rho 2, then this is going to be rho 2 tensor rho 1 on V, and this is on S and this is on V. So this is going to be equal to essentially rho 2, which was the state of V originally. Okay, so in particular, what I could ask is, well, what is the virtual temperature, the bias, etc. of the system? So now this is a bit tricky. If the energy of S is the same as the energy of V, that means the Hamiltonians, where did I draw it? Yes, if these Hamiltonians are of the same size, so ES is equal to EV, then everything is the same. Then beta S prime, so the final virtual temperature of the system, is just what the virtual temperature of V is in the beginning, because it's just taken the state of V. But if ES is not equal to EV, then we have something tricky, because what we have flipped is the states. So what we have switched are the populations in the various energy eigenstates. But remember that the virtual temperature depends on more than the state, just the populations. It also depends on the energy difference. So we know that the initial virtual temperature of the system is defined by, well, in our notation, so it's P1S upon P0S, which what we took it to be is just 1 minus P0S upon, oh, sorry, no. This is not, this is e to the minus beta Vs Es is equal to 1 minus P0 system upon P0 system. So then we should have e to the minus beta Vs prime, the final, I apologize. I have realized that I should be more careful with what I pick. So this is S and this is S prime. So the initial virtual temperature, what's the real temperature of the system, is given by this formula. The final temperature will be given by yes P1V upon P0V, because the final populations of S are the initial populations of V. But this is given by e to the minus beta V EV. And so the actual result that we have is that beta S prime is equal to beta V times the ratio EV upon ES. So this is important. If the energies are the same, then all we do is we just flip the virtual temperatures. But if the energies are not the same, then actually the virtual temperature of S does not just become the virtual temperature V, it changes by this ratio. This is actually kind of useful because one of the simplest ways you could think about cooling down a system, which is the same as increasing beta. So remember, cooling down a system means decreasing the temperature T, but beta is the inverse of T, so we increase beta, is by simply swapping the state with another state that has a higher energy and the same virtual temperature. So what do I mean is the following. Imagine that we picked ES to be less than EV, but we picked beta to be the same. Pick beta S equals to beta V, and then we did the swap. What we would have is that beta S prime is equal to beta V times EV upon ES, which is just the original beta S times EV upon ES. So if this is greater than 1, then beta S prime is greater than beta S. So if we take two states that are the same temperature, and then we swap them, essentially the smaller energy gap is going to look like it's become colder now. And the inverse goes for the other one. The other one is going to look like it heated up. Right. So that's the first conclusion we can draw. The next conclusion that we can draw is we can ask, well, how did the average energy change as a result of this operation? Now, if EV is equal to ES, then there's no change. And the reason is very simple. If EV is equal to ES, then the Hamiltonian HSV is just 0, let's say ES again, because EV is equal to ES, and then 2 ES, state 0, 0, 0, 1, 1, 0, 1, 1. So what we see is that we have a degenerate subspace here. And of course, combined with the knowledge that U is equal to 1, 1, 0, 1, 0, 0, 1, what we immediately see is that the unitary is only non-trivial in that degenerate subspace. And this is the same as saying that HSV and U commute if, so this is the U swap, commute if ES is equal to EV, which kind of makes sense if you think about it intuitively. If you have two qubits that have the same energy gap, then swapping them is an energy preserving operation because they have the same energy. So you cannot really change the energy by swapping the states. If ES is not equal to EV, however, so if ES is not equal to EV, then this is not energy preserving. And the energy does change. So the initial energy which is, I could write it as trace of the total Hamiltonian HSV, rho SV is, now I'm going to do this once in detail, but effectively we wouldn't need to usually, because remember the Hamiltonian is just the sum of the individual Hamiltonians unless I have interactions, which I do not have at the moment. Rho S tensor rho V, and this you can split as trace of, I just use the sum, HS V rho S tensor rho V plus trace of HV rho S tensor rho V. Right, and now here we can already, in each of them, we can already do a partial trace because I have identity. In the first case, I have the identity operator on system V. So the identity operator on system V times some random density matrix on V. If I just take the trace over V of that, I'm going to end up with 1 because the states are normalized. So I can already trace out that part, and I'm just left with trace of rho SHS. And the same way in the other one, I'm left with trace of rho V HV. And this, if I expand this out, each of these traces is, remember, the sum of the probabilities in the nth energy eigenstate times the energy eigenvalue. So this is, and we use the convention that the ground state always has 0 energy. So this is now just P1S ES plus P1V EV, which let's just stay with the ground state populations for simplicity's sake. P0V EV. So this is the initial energy. Now I can go through this the same way and find what is the final energy, so rho SV prime. And I go through the same steps, but again, I'm going to end up with the same result, except that the states, the populations that are on the different energy eigenstates have just been flipped. And so in the end, what I'm going to get is 1 minus P0V times ES, because that the population now on the excited state of the system is what used to be the population on the excited states of V in the first place. And the same thing on the other side, flipped EV. And so the change in energy, so delta E or delta E average, which is the difference, which is E prime average minus E average, I can see now is ES minus EV times, so this is the prime, rho 0 S minus rho 0 V. Right. I always have to look at this a second time to make sure I didn't get the sign wrong, but yes, that's the end result of the change in energy due to the swap. This is also kind of very nice to understand. If we look at this, this is the energy difference, and this is the population change. Because if I start, so essentially I started with the system having populations P0S in the ground state and 1 minus P0S in the excited state, and I changed it to P0V and 1 minus P0V. So the change in population is essentially given by this difference, P0S minus P0V. So essentially the way to understand this is I shifted this amount of population at this energy cost, and therefore my total work, the energy cost of this operation, or the energy difference of the operation, is given by the product of these two things. The reason I sometimes refer to this as the energy cost or the work cost is because remember by the first law of thermodynamics, or the first law of physics in general, that energy is a conserved quantity, which means that if I apply a unitary operation on two systems that ends up changing its average energy, then whatever was the machinery that applied that unitary operation must have had its energy decrease. So the energy has to come from somewhere external. And so that sort of represents the work cost of doing this operation, that whatever machinery did this unitary had to have that much energy and had to have decreased in that amount of energy. Right. Are there any questions? Nope, not so far. All right, very good. Okay, so this was rather straightforward. Oh, yes, there's a question.
Scroll up when you started explaining this topic.
Yes, scroll up to when, yeah.
Here, I think, below.
Yes.
Yeah, here.
Mm-hmm.
Could be, well, no, never mind. I will check your notes and I will ask you directly.
Okay. Could you say what the confusion is about?
I don't remember clearly, but I think that there was a mixing between the energies that I did not understand, but I will ask you anyway in forum or whatever.
Okay. All right. Okay. Yes. Yeah, for sure. I should have called the other system M so that there was no confusion between virtual qubits and machines and stuff. So I apologize if I have at some point made an error because of the notation. But yes, the lecture notes I think should not have these errors, and all of this is repeated there. So yeah. But yes, please do ask me the question in whatever fashion when you think about it. Okay, so this is all very nice. We have if you swap two real qubits, then the system just flips, and whatever the state of V was, you now have as the state of the system. But one of the things that we realized is, and the reason we did all of that composition of virtual qubits is that sometimes we're not able to design real qubits at a particular temperature, but we can design virtual qubits at a certain temperature by taking a tensor product state and having a subspace in that look like the temperature that you want to see on your virtual qubit. So what would be more interesting to us is if we try to do the swap between a system qubit and a virtual qubit that is part of a larger system. And this is a bit more involved. It has essentially the same, some features are exactly the same, but some features change a little bit. So what is our new scenario? Our new scenario is that we have a Hamiltonian of a system, and the system is just a qubit, and we have a Hamiltonian of V, which is some larger system. We pick the virtual qubit here, and now we do the swap, the same swap that we were doing in the last case. So this is another nice way of writing a swap, because effectively, when I say that 0, 1 goes to 1, 0, it's the same as saying either when one of them goes down in energy, the other one goes up in energy, or vice versa. That's, well, one of them, the terms in the unitary are both this, the one-way flipping, and the Hermitian conjugate, which is the flipping the other way. So this is why this is another use of the energy level diagrams to write down these unitary operations. Okay, so this is what we would like to do. Now we have to be a bit more careful here because the density matrix of V is in general more complicated. So rho s is still going to be P0s, P0s and 1 minus P0s, 0, 0. But rho V now is going to be of the following form. I'm going to take a block diagonal with respect to the virtual qubit that we have. So there are lots of elements that we know nothing about, but there is at some point an element which I will call P, well, let's call this Pi V, and then other elements we know nothing about, Pj V, other elements we know nothing about. And taking it block diagonal means that in the same rows and columns as the elements that we are focusing on, there are no other non-zero elements. So this is block diagonal with respect to that 2-qubit subspace. Okay, and now I want to do the equivalent of the swap operation, but my swap is only swap the system qubit with just this qubit subspace. So the manner in which the swap is done, the unitary operation is going to look like it's got ones everywhere except for these two states. And these two states correspond to the following. This is the state 0j, and this is the state 1i on system and V. 0j, and 1i, system and V. So another way of writing this is to say that the unitary is equal to the swap between these two states. So it's uj goes to 1i plus 1i goes to 0, so 0j, sorry, plus the identity operator on the rest, so on all of the other states. Or another way of writing it is just to say it's just the identity operator, which will give you ones everywhere. And then you want to take away the ones in the diagonal elements. So you remove the diagonal elements. Sorry, 1i, 1i. And then you add the X operator in that subspace, which is the one we've just written down. Yeah, so this, in fact, is just basically a way of writing identity on the rest. Yes, so in summary, we have a larger dimensional system now for V, but we still want to do the swap between S and a virtual qubit within that. And okay, so right. So now let's do this slowly to see what happens. So we have the state rho S tensor rho V, which we can write in the following manner. So I have PS 0, 0, 0 on S plus 1 minus PS 0, 1, 1 on S. And this is tensored with the state of V. And the only thing I know about the state of V is I have a PI V on II of V, PJ V on JJ of V. And then I have a rho V rest, which just reflects that the rest of the density matrix that I haven't included by writing these two terms. So remember that this one does not have, there is no contribution from the states I or J, because as we've set all of the elements that involve I and J, except for the two elements that we've listed, to be 0. Okay, and then I do U rho S tensor rho V U dagger, which gives me a rho SV prime. Now, unlike in the case of two real qubits, it's not the case that these two states just flip, because in fact you have part of the state of V that doesn't actually participate in this unitary operation, that doesn't get affected by this unitary operation at all. So let's see what happens. We have that rho SV prime is equal to, what we do have is that in the subspace that we have isolated, the 0j, 1i subspace, those states do flip. So what we end up getting is, well, actually, let me write this down. Let me do one more step to make this very clear. Rho S tensor rho V is equal to, if I was to write this down in full, it would be, so now I'm going to expand these two brackets. So I'm going to get P0S, PIV, 0i, 0i, SV, plus P0S, PJ, V, 0j, 0j, plus 1 minus P0S, PIV, 1i, 1i, and finally 1 minus P0S, PJV, 1j, 1j. And then the final part is just rho S tensor rho V on the rest, which we don't care about. Well, we care about it, but it doesn't get affected by this unitary operation at all, because as far as that is concerned, the unitary operation is identity. Right, so what is our unitary operation? Our unitary operation is essentially to flip these two elements. It flips the 0j with the 1i. So what happens is that our final state, rho SV, sorry, one color. Our rho SV prime is simply going to flip those two. So this remains the same. This remains the same. So this one now flips. This is now 1 minus P0S PIV with the 0J plus P0S PJV with the 1I plus 1 minus P0S PJV 1J plus rho S tensor rho V on the rest. So that's the final state. And this is something you can verify by multiplying these matrices through. What we care about, of course, is the final state of the system. So what is rho S prime? So this is equal to the trace of rho SV prime traced over V. Now remember the trace operator when it acts on a projector. So if I say trace over V of this operator, for example, I on V, this is just equal to the inner product II, this is just 1. So the trace of any projectors where the bra and the ket is the same state, is the same and it's the normalized state, is just going to be 1. So we can now do this in detail and say that rho S prime is equal to. So in the first case, I get rho S IV, and the trace of that operator is on the V part is just 1. So I get that on S. The next one is going to give us 1 minus P0S PIV 0 on S again. Then we're going to get P0S PJV 1 on S, and finally 1 minus P0S PJV 1 on S plus, and now this is interesting, we get a rho S tensored trace over V of rho S, the rest times V. So what is the trace of the density matrix of V without the elements that we've sort of excluded? So remember, the state of rho V is a general state, and it has these two elements that represent the virtual qubit. So rho V rest is essentially the same density matrix, but with these not appearing. So this is now going to be, this is 1 minus PIV minus PJV. Okay, so this can be further simplified. We can combine the terms which have the same projector on S to get PIV 00S plus PJV 11S plus 1 minus PIV minus PJV, and that's just multiplied by the original state of what S was. This is now, at the moment, it doesn't look like a very good or understandable form, but now we can use what we have learned about virtual qubits. So remember, if I have a virtual qubit that is defined by these two populations, Pi and Pj, and this is delta E Ij, then what I can say is I can define the norm of the virtual qubit to be the sum Pi plus Pj. So this is NV, and the bias of the virtual qubit is Pi minus Pj upon Pi plus Pj. Okay, sorry. Right, so this is now, I can write the final state, rho S, as, now I'm going to do something, a mathematical trick. I'm just going to multiply and divide by Pi Pj first of all, so that in the first bracket I have PIV upon Pi plus Pj, VV, VV, with the 0 state, plus PJV upon Pi plus PJV, V, 1 state, plus 1 minus Pi minus Pj, V, rho S, which is equal to, and now I'm going to write this as NV times tau S times rho s. Now, what is this tau s beta v? So what you see in the brackets is effectively what the thermal state of that virtual qubit would be if it was actually a real qubit. So effectively, when we have a virtual qubit that sits in a larger dimensional subspace, the only difference between that and the real qubit is that its norm, the total population there, is not 1. But we can always take away that subspace and renormalize the probabilities in that subspace to make sure that they add up to 1, and then we end up with a real, essentially the state of a real qubit. And the reason it has the same virtual temperature is because when we renormalize it, we multiply both of them by the same factor, which is this factor, or divide it rather by the same factor, which is the norm. So the ratio between these two is still Pj upon Pi, which is still the original, still the original Gibbs ratio. So this therefore reflects sort of the normalized state of that virtual qubit, not the actual state of it, not the actual properties, but the state as if we promoted it to the status of a real qubit. Okay, so the way to understand this is actually quite simple. We have a system rho s with probability NV. We take it to the thermal state that it would have if it were to take on the temperature beta V of the virtual qubit. And with the probability 1 minus NV, it's unchanged. Another way of saying this is that NV is essentially the total probability that your system V is actually in the subspace of that virtual qubit. It's the sum of the probabilities of being in that subspace. So NV, with the property NV, you will find the system in that subspace, in which case the swap works just like our real qubit swap. So it's a full swap. Or you will not find it in that subspace, in which case the swap does nothing. So the final state that we have ends up being a convex combination or a mixture of these two cases, as if you had the full swap with a real qubit versus having done nothing. Another way of understanding this formula is we can take the difference rho s minus what I've labeled as tau s beta v, and this will be now NV minus 1 tau s beta v plus 1 minus NV rho s, which is 1 minus NV rho s minus tau s beta v. So in other words, the difference, this is rho s prime, the final state, rho s prime, that's the final state. Right, okay, I didn't make that mistake up. Right, so the difference between the state of your system and the sort of the normalized state of the virtual qubit you're swapping with decreases when you do the swap. It doesn't completely go to 0, which is what would happen in a real swap. That is where NV is 1. And so you immediately get to the final state. But it also does something. It sort of takes you partially from your initial state towards the normalized state of the virtual qubit. Okay, I pause here. Are there any questions? Because this is a critical thing, so it's important for everyone to understand what has happened quite clearly. No questions.
Just one question. What do you mean
Yes.
that you don't find the virtual qubit in the state that you want?
Aha. So what I mean is, okay, actually, there is another way of saying this, which I will do now. So this state here, let me just. So this state here, I can write in the following form. I can write it as PIV plus PJV times this density matrix, which is 0, nope, cancel, 0 everywhere else, PIV upon PI plus PJ, then you have zeros, PJV upon PIV plus PJ, and then you have zeros, 0 everywhere, plus what I have remaining, which is 1 minus PI plus PJ, V, of course, times, well, actually, no, let me not write it as that, just plus, I will say, now I just have a 0, 0, 0, 0 here in these places, and everywhere else I have the rest of the density matrix that I didn't write in the first place. So what I've done is I've just said, let me write it as the sum of the part that's just in the virtual qubit subspace plus the rest of it. And the reason this is useful is because when I write it in this form, this is now, this first part is now NV times, it's not exactly tau beta V, but it is like the thermal state in that subspace. So let me just call it rho. Let's call this tau V. Oops, sorry. Let's call this tau V, which refers to these two elements with zeros everywhere else, and this is rho as the rest. Then U acting on rho S tensored this sum. So NV tau V plus rho on the rest, U dagger is equal to U rho S tensor NV, well, NV can come out actually because it's just a number, NV tau V, U dagger, plus U rho S tensor rest on V U dagger. So what you see is that you effectively get the combination or the mixture of two things. One as if the state is there in that subspace, and the rest is if the state was not in that subspace. And the probability of these things happening is the probability of the first case is NV, which is the total population in that subspace. And the probability of the other case happening is the trace of this rho rest, which is the sum of all of the diagonal elements except the two that we removed to put it in tau V. So this is 1 minus PIV minus PJV, which is 1 minus NV. And so this is what I mean by, so this is a bit hand waving. It's I think the experimental way of saying this is, if I was to make a measurement that would essentially check whether my system V was in this subspace or not. So the two measurement operators would either be the projector on the subspace and the projector on everything else. Then the probability that I get the result it's in the subspace is NV. And the probability that I get the result it's not in the subspace is 1 minus NV.
Okay, thanks a lot.
Okay, right. So if there are no further questions, what I'm going to do is, okay, so one of the things to mention is that because rho has this form, what is this form? Yes. So because the state rho has this form, the same thing we can check, and this is a little exercise you should do, is to check that the final bias as well, ZS prime minus ZV, which is the bias of the virtual qubit, also has the same relationship, 1 minus NV times ZS minus ZV. So effectively, all of the properties of the state of the system move closer to that of the properties of the state, the normalized state of the virtual qubit, but only partially there. And how close they move depends on the norm or how much population there was to be in that virtual qubit in the first place. Okay, so now this is useful, but we are going to continue with something even more powerful, which is resetting and repeating, which is the following. So the unitary that I just did, which is a swap operation, has the property that if you do it 2 times, you end up going back to the state that you originally had. And the 2 ways of seeing that is that the square of the unitary is identity, because it's essentially in a qubit subspace, you have the Pauli X operator, and we know that the square of that is identity. And the other way of saying it in words as well, it's a swap operator. So if you swap 2 states and 2 energy levels and then swap it again, you end up going back to your original state. So doing it repeatedly doesn't do much. It just oscillates between the state that we had to start with and the state that we get after one swap. But what we can do, and this is the basis for a lot of things in thermodynamics, is we can say, well, before I repeat the swap operation, let me return the state of V to what it originally was. Because the way most thermal machines work is we're going to have a system. We're going to design a virtual qubit to have the properties we like. And we're going to have a way of maintaining this system, the machine V, to have the properties even after we interact with the system. So effectively what this means is after we perform a swap operation with the system, we then reset the state of V back to what it originally was, and then we decide to swap again. So what does this mean? This is the concept of a reset channel. And the reset channel is very simple. It's a map that acts on rho AB. So it's a map AB. And it effectively gives you the state, the reduced state on A. So remember the trace out of, if you trace out B, we get the reduced state on A, tensor with some state on B that we call a reset state. So what does this mean? It means we had some arbitrary joint state of A and B. We then traced out B, so we'd have the reduced state of A, and we replaced the system B by a new sort of copy of the state that we want, which is the reset state. So in our case, what we're going to do is we're going to take, so our reset is going to take rho SV prime, whatever it is, and it's going to replace it by, we trace out V to find the reduced state on the system, and then we tensor it with rho V, which is the state of V that we started off with in the beginning. So this is our reset channel for the, yes, to reset V back to its original state before we do another swap. And so now we ask, well, what is going to happen when we do this? Imagine we now have, we already have done one swap and we do a second swap. So the first thing to note is that what this looks like is rho S prime. Just by definition, we've called this the reduced state on S after swap operation as rho S prime, tensor rho V. And so now we do the unitary, the swap unitary on this, rho S prime, tensor rho V, U swap dagger. We get a new state, which we can call rho SV double prime. And then that gives us a rho S double prime, which is the trace over V of rho SV double prime. And so now the question is, what is rho S double prime? And well, the nice thing about writing our final state in such a nice form before is that we don't have to go to the entire calculation again, because we knew that, so we already have this form here, that the difference between the final state and the normalized state of the virtual qubit is just given by a simple number times the initial difference. So we can use the same thing here. We're going to say that we know that if we apply the same operation again, we will get the rho S double prime minus this thermal state of the virtual qubit that you're trying to reach is going to be 1 minus NV times the initial state. But now the initial state of the second swap, remember, is the final state of the first swap, minus tau S of beta V. And this in turn, we know what the difference after the first swap was, and we can substitute that here. This is just going to give us 1 minus NV squared times the original difference rho S minus tau S beta V. And as you can imagine, after n steps, if now I repeat this n times, so I swap, then I reset V, and I swap, and I reset V, and I keep doing this n times, I'm going to get that rho S after n steps minus tau S beta V is going to be given by 1 minus NV to the power n, sorry, rho S, the original difference minus beta V. I can also call this rho S0 to signify that it was the state right at the beginning before any steps had been applied. Right, so what is this expression? This is essentially a discrete decay towards a steady state. And what we mean is the following. So what is the limit as n tends to infinity of 1 minus NV to the n? This is equal to 0 because 1 minus NV is somewhere in between 0 and 1. So we're assuming that NV is not 0, because if NV is 0, that means that our virtual qubit just doesn't exist. There's no probability of being there at all, and every swap will do nothing. But NV is not necessarily 1 as well, because it may have population in V that's not in this virtual qubit subspace. So it's a number between 0 and 1, and any number between 0 and 1, if we take an integer power of it, we will get closer and closer to 0, the limit being getting exactly 0. So as a function of n, essentially you get something that decays towards 0. And this is 1, 2, 3, 4. This is 1 minus nv to the n, which means that the limit as n tends to infinity of rho s n is equal to tau s beta v. So what we've done effectively is we've showed that if we have, so to recall, if we had a real qubit, a single swap would simply take the state of the real qubit and put it on our system. What we've shown here is that if we have a virtual qubit, then of course a single swap is not enough for our system to look like the thermal state that virtual qubit looks like it has. But if we keep repeating the swap, then in fact, the net effect after a long enough time is to simply be the same as if the virtual qubit was a real qubit. So whatever virtual temperature, or at least the populations on that subspace, whatever we start off with on the virtual qubit, they will eventually be shown to, well, they will eventually be induced on our system after a long enough number of steps. So this is sort of the first example that you have of some sort of a thermalization procedure where we have a temperature that we connect our system to, and we have a process that keeps repeating. In this case, it's a discrete process because we do a unitary and we reset, and we will discuss later examples of a continuous process. But this is a process that keeps repeating that will eventually take your system to that desired temperature or to that desired state. So it's the first example of such a procedure that we have. Just as in the case of one swap, this also holds for the bias of the system. So remember, the bias is the ground state population minus the excited state population. So the bias after n steps minus the bias of the virtual qubit is going to be 1 minus nv to the n, the original bias, minus the bias of the virtual qubit. In the case of the bias, because these are just numbers and these are not density matrices, I can in fact write this also as a ratio. So the ratio of this difference to the original difference is 1 minus nv to the n. Okay, right, I stop here. It's perfect timing. Actually, are there any more questions? None at all? Okay, so then, oh, yes.
One still regarding before, I think about 20 minutes ago, when we talked about connecting the system to our virtual qubit, there the system with maybe a bigger space with the virtual qubit, all discussion would also work if the state rho v would be an incoherent state, in the sense that it's just a, say, classical density matrix. Is there, so it doesn't use like the quantum properties where we have off-diagonal entries for the density matrix rho v.
Indeed, indeed.
Mean that we could also use as our system where you have a virtual qubit some kind of classical system to cool down our quantum qubit and therefore connect these two, or do I somehow misinterpret here?
No, you're absolutely right. So in fact, yes, you're right. You could use a classical system in order to do that. In fact, one of the general statement that I can make actually is when we're working with incoherent thermodynamics, where we deal with incoherent states, or at least always in incoherent subspaces, everything is effectively classical. So the only quantum nature is the fact that you have quantized energy levels. So it's not a continuous spectrum of energies, but there is no influence of entanglement and quantum coherence to be seen. So that's the the advantage as well as the disadvantage of working with incoherent thermodynamics. You don't have you don't have influence of coherences. So indeed, all of this could be put in classical terms. I could write the swap operator classically as well. Having said that, one case that you might run into is where the state of the system to begin with, for example, is not incoherent. So I did this example here where the system starts out incoherent and the virtual qubit that we're dealing with is also incoherent. And this was simple, but what you could also consider is that your system starts out with an arbitrary density matrix. So you have off-diagonal terms as well, and your virtual qubit is still incoherent, and then do the swap and repeat it. And what you find is that in addition to the diagonal elements slowly moving towards the induced populations by the virtual qubit, just like we've done here, the off-diagonal elements keep decreasing. Because what happens with the swap is that some of these correlations are you sort of build up correlations between the system and V, quantum correlations, but every time you reset the state of V, you lose these quantum correlations. And so those coherences decrease with the number of operations. So in general, it is important to also keep track of the coherences. I do this example here for simplicity, but you could have situations in which there are coherences and you have to sort of keep track of them. Not between different energy eigenvalues, or at least if you have different energy eigenvalues and you have coherences there, then that's a completely different scenario, because then, as I discussed in the first lecture, we must have clocks that are present as well and included in the description that keep track of these phases.
Okay, I think possibly the same thing that happened last lecture happened now, where the audio stopped working, maybe because my earphone battery ran out of time. But in any case, this is a good point to conclude this time's lecture. In the next lecture, we will introduce the notion of passivity and have the first example of a real thermodynamic resource theory. Another thing to say, I have sent out an announcement on the forum in Moodle that this week's office hours will not be tomorrow, but will be on Friday instead at the same time, 14:45 till 15:30 in the afternoon. So if any of you would like to ask questions, please come along on Friday instead. Right, and with that, I wish you a good evening and see you in the next lecture. Thank you very much.
Thank you. Bye-bye.
Thank you. Bye-bye. Thank you for the lecture.